Hi, and welcome to this Grasshopper data manipulation course. Today we're going to explore some functions that are present in Grasshopper but that normally standard users or new users tend to leave aside in the attempt to create some fancy design. But in the end, this is something that it's not a good approach, let's say so, as data manipulation is actually the only way that users can find a way to create basically whatever kind of design or application they might want to create in Grasshopper. So data manipulation is basically the true way of getting anywhere with Grasshopper. Remember that Grasshopper is not actually a design tool. It's actually a visual scripting tool. So you will be coding inside Grasshopper, not designing inside Grasshopper. So coding is basically data manipulation at its best, because if you think about all these components that you can already see in the canvas in Grasshopper, if you think about them as functions, then each function has its own input and produces its own output. And the input and output is basically made up of strings. And these strings are basically data vectors. So if you think about working with Grasshopper in terms of coding, you would be dealing with lists of data. And that's the usual way that you work inside Grasshopper. So trying to avoid this kind of situation is like pretending to, I don't know, driving without a driving license, basically, or something like that. So today we are going to start exploring the Grasshopper data manipulation tools, which are basically, well, as you can see, there are plenty of tools, and these are not all the tools that we should study, but they are the most important. Most of them are can be found inside the sets toolbar in Grasshopper interface. There is just one component that I will be using that is that you can find in the params toolbar, which is the param viewer. So this is something that we will discuss in a few minutes. But all the rest of these components, of these functions, you can find them into the sets toolbar, which is one of the scariest toolbars in Grasshopper interface, which is something that standard user tends to skip, preferring to directly draw or model something. So we will focus on this. And talking about this toolbar, you can see that there are several groups: list, sequence, sets, text, and tree. We will not be talking about the text group because it is basically pretty straightforward. We will be discussing the list, sequence, sets, and of course the tree group. Now for this first section, probably we are going to cover the list, sequence, and sets groups of comments, and in the next session, which will be also the last session, we will discuss the tree group of components, which is somehow a little more tricky and complex. So here you can see that I have prepared the file for these first sessions. This is the list set of components, this is the sequence set of components, and this is the sets set of components already analyzed in details. While here you will find, for example, in my definition, there is this, these are all the list tools, these are all the sequence tools, the sets tools, and the tree tools that we will be discussing in the next session. So let's start with the list tools. You can see that in Grasshopper also groups are subdivided into subgroups. You can see this horizontal separator here, and I have maintained this kind of structure in this grouping in my definition. So you will find the first set of list components, which is this one, and then the second one, the third one, and the third one and the last one, which is this lists manipulation for Grasshopper. So let's go and see how this works. So first of all, a list. What is a list? A list is basically a set of data. You can think about a list as in a way that it might sound unusual, but if you, for example, take this value here, which is a panel containing just the number 0, this is already a list of values. Of course, it contains just one value, but this can be seen as a list with one single value. One thing that we can do when we have this kind of component here, which is the panel. The panel can be used for several tasks, okay, but it can also be used to create a list directly. If you want a panel to convert a panel into a list, you might want to right click on the panel and hit the multi-line data option. This is actually a way for converting a panel into a multi-line data, which is basically a list of values. The difference, if you don't do this, is that if I, for example, create a panel and go inside the panel and start typing 0, enter 1, enter 2, 3, 4, 5, 6, 7, 8, and 9, all separated by an enter key. Now these, as we have used the enter keyword, Grasshopper sees this content as a text. So you can see, for example, that if I take an integer container or a text container and plug this into the integer gets angry, it gets red, and it says basically it contains null objects, and it says cannot convert a text to an integer value. While if we plug this into the text component, you see that this is actually containing all the text, which is basically made up of separate lines into one single, let's say, section. So you see that there is only one index in this list. So in this list, we only have one item, which is 0, 1, 2, 3 with enter keys. Now, if we right click on this panel and convert it into a multi-line data, then you can see that this is the typical representation of a list of values. There is the so-called indices and paths. Okay, so the indices are the numbers that you see here in the first column. For each index, you will find an item. Okay, while this is the path of this list, which is important when we will start to talk about trees. Then this path will become more relevant than in case of lists. In case of lists, this affects some lists interactions. So it's important also to consider the path when working with lists, but it's not as important as when you are working with data trees. So in this case, for example, you see that also the integer starts to work properly because each value is now a separated item with respect to the other ones. So it's not just like a text where lines are separated by an enter key. These are all separate data, each with its own index. So integer is actually receiving each number in one single line of the list. So that's why you see that both objects start to work properly. Of course, this integer is interpreting this value here as a number, while the text container is interpreting this value as a text. Okay, but in the end, when you work with numbers or text like this, you can also consider them as numbers, even if you pass them through a text component. Exactly. So this is how you can create, for example, a series using a panel. Okay, so here I have created a series of values using the series component, starting with 0, with a step of 1, and with a count of 10, which is the default series component in Grasshopper. You can find it in sequence group here, and it is called series. We are just let's say, anticipating this component because it is useful, because we want to work with series, and this is a very quick way of creating a series of value, and this is the list. You see that this list has a different path with respect to the previous one, which was created directly. Normally, the path increments the number of indices that you find here according to the number of operations that you perform over a set of data. So in this case, for example, this series was creating, let's say, it's a second level list of values, okay? So that's why you see two numbers here in the path. This is something that, I repeat, we can explore later on during this first session eventually. So this is the list of values, and here I am using the component that I was telling you a few minutes ago, which is the param viewer. The param viewer is absolutely important when you want to analyze and study a data structure in Grasshopper. So you see that the param viewer can be used in two different ways. There is a graphical way, which is this one, and there is an analytical way, which is this one. Okay, normally I prefer the analytical way because it gives you some interesting and relevant information, while this is something that, yeah, it looks nice and it looks fancy, especially when you work with very complex data structures like complex data trees and so on. But this configuration here, this aspect gives you more relevant information, such as, for example, now the path of our list, which is one single branch, of course, that's why data with one branches, and the amount of items that are present in this branch, or rather in this list at the moment. And you switch between these and these by double-clicking the param viewer component, like I'm doing here right now. I will be using this list, well, let's say plenty of times in these first sessions, because as we will be working with data manipulation components, I will use these as a reference list in order to perform several operations on these sets or set of data. So first of all, you can see that in this list group, these components here, which are cross-reference, shortest list and longest list, are in the last positions, but I want to discuss them first, so that's why I placed all these examples here. So you can see that in this first group here, you will find this component, which is the longest list, and then there is this other group here where you will find the shortest list. And then there is this other one where you will find the cross-reference component. Now, why are these components so important? Because they affect the way that Grasshopper handles the interaction between lists of values. What's the meaning of this? Well, we will analyze these examples in a few seconds. Just to have a clearer idea, let me create the same example, but with a step-by-step, so we can understand what's happening there. So basically, let's create a point container and say I want to set multiple points in this container, like for example 1, 2, 3, and 4. And then let's take another point container and then say I want multiple points like 1, 2, 3, 4, 5, 6, 7, like this. Now what happens if I want to create a line between the first set of points and the second set of points? So like creating a line component from start point to end point and then connecting the two containers. Now this is what happens normally in Grasshopper when you have one component, like the line in this case, generating the interaction between two sets of data. So in this case, two lists of points. Now we have, let's also detail of all this process, so we won't miss anything. We have these two different lists here interacting inside the line component. Okay. Now the first list, which is this one, only has 4 values inside, while the second list has 7 values inside. Just a quick observation, you can see that as this is basically coding, visual scripting, you will see that the first value, the first item in one list has index 0 and not 1. So 4 items range from index 0 to index 3, while 7 items range from index 0 to index 6. So this is the standard annotation for indexing in Grasshopper lists. Okay, so what happens when you have this kind of interaction inside this component, this kind of component here between two different lists? Basically, the interaction is always one-to-one in Grasshopper. So if we take this first set here and this second set here, what happens is that item number 0 is interacting with item number 0 of the second list, like this. And then there is 1 with 1, 2 with 2, 3 with 3. But then you have 4, 5, and 6, which are basically spare values if compared to the first list. The first list only has n equal 4, while the second list has n equal 7. So what happens in this case? In this case, Grasshopper uses as the standard method for lists interaction the method that is called the longest list. So the longest list states the number of interactions that are created in this kind of relationship. Okay, so Grasshopper will create 7 lines because the longest list has 7 items. How can Grasshopper create 7 lines? Well, what happens is that index number 3 of the shortest list will interact also with index number 4, 5, and 6 of the longest list. So basically, if we want to represent this graphically here between this list, you will have some line 0, 0, 0, 1, 0, 2, 0, 3, and then 0, 0, 1, 1, 2, 2, 3, 3, and then you will also have line 3, 4, 3, 5, and 3, 6. So this is what's happening here, as you can see graphically. Okay, so you will have the first point of the first set interacting with the first point of the second set, second with second, third with third, fourth with fourth, and as there is no fifth, sixth, and seventh point in the first list, the fourth point will interact with the fifth, sixth, and seventh point of the second list, the longest one. So this is how Grasshopper works normally. And normally means that when you have this kind of interaction between two different sets of data, like one having 4 and one having 6, 7, Grasshopper will use the longest list method by default. So longest list method means that if we go into the list group of components, it is this one, the longest list. What does it mean? Let's take a look at what happens if I plug the shortest list into A and the longest list into B. It can be also the opposite, but it doesn't change. It's absolutely identical. And if we do this, you see that nothing happens. The lines are traced exactly like if we didn't use the longest list. But what is the longest list doing is this. If you take a look at list B, which is basically the transformation applied to list B, which was the longest one, there is no transformation because the list B is already the longest one. While list A, which was the shortest one, becomes this. And apparently you have, well, actually you have 7 values right now. But if you take a look, the fourth value is repeating in order to reach the length of the other list. So basically, Grasshopper in this way is able to create interactions between one element of the first list and one element of the second list. This is something that Grasshopper does automatically. Okay, so the longest list is the standard method in Grasshopper. Why there is the longest list component if this is something that already happens normally in Grasshopper? Because the longest list component has several ways of creating this kind of change in the shortest list. So if you go and right click on when you see this kind of black description at the bottom of one component, it means that you have some options inside this component, and these options are normally accessible via the right click button. So if I right click here, you see that this component is set to work with repeat last option, which means that basically given the shortest list, this longest list will repeat the last element of the shortest list as many times as needed to reach the length of the longest list. Okay, so this is what happens if I repeat last. Now I don't care about the graphics right now. What I want to point out is the difference. So if I take another longest list and say repeat first, what I will have is always a list of 7 values, as you can see, but what is Grasshopper repeating right now is the first element, the first item, and not the last one. Okay, so you can see that this 2.83, 16.97 repeats 1, 2, 3, 4 times, including the original item, and then you have the 5th, 6th, and 7th element of this list A. And then there is, for example, let's copy paste this directly. Okay, so instead of repeat first, repeat last, it's okay. Now interpolate is something that is very interesting, because interpolate tries to repeat the items according to the length of the longest list. So it's like stretching the shortest list in order to make it as long as the longest list. So you can see that in this case Grasshopper is repeating 2 times the first item, once the second item, 2 times the third item, once the fourth item, and so on. Okay, so you see that there is 2, 1, 2, 2 in order to have 7 items like in the longest list. This is something that has some interesting graphic consequence. For example, if I take the interpolate and take the list A and list B, you see that you always have repetitions, repeated lines, okay, in the points belonging to the shortest list. But you see that these repetitions are distributed along the series of points or of lines. Okay, so it's different if I select repeat last. You see that it's the last point that is creating several connections to the second list. If I repeat first, I have several connections starting from the first point. But if I interpolate, you see that multiple connections are spread all over the shortest list. And you see that you have 2, 1, 2, 2. It depends on the amount of data that you have in the first and the second list of values. Okay. There is also the wrap and flip. It means, for example, if you take a look with a panel, which is always the best way of analyzing the data that is coming up, you see that in this case, in order to reach the length of 7 items, Grasshopper is repeating starting from the first item once again. So you see 2, 8, 14, 19, and then 2, 8, 14. And if the second list had 8 elements, you will also see 19, of course, and so on. Okay, so this means wrapping the list of values. And you can see, for example, that this point is connecting with this, and then this with this, this with this, and this with this, which are the first 4 connections. And instead of connecting these with the other 3 here, Grasshopper is starting once again to connect from this point with the 5th point of the second list, second with 6th, and third with 7th. Okay, so this has also interesting graphic consequences in terms of interaction inside the line component. And finally, there is the flip. So you see that flip is actually doing the same, but you see that there is 2, 8, 14, 19, 14, 8, 2. So it's coming back. Okay, and this normally this is something that that you don't want to do when working with graphic components like a line in this case, as well as normally you don't want to repeat last or first if you want to get some interesting graphic result. You might want to eventually use the interpolate component eventually, but it depends also always depend on the amount of values that you have in the 2 data sets. Okay, so this is what happens with this longest list, and here we have some explanations. You see that this is basically what we were just seeing right now. So I will turn off the preview, and then you have repeat last, which is the standard Grasshopper behavior. Repeat first, interpolate. Now in this case you see that the design is more balanced because we have 4 and 6 points. And then there is the wrapping and flipping. Okay, now if we want to try to design something using this this property of the longest list, eventually we might want to create a line component and then set one line here. I will use the grid snap in order to have a more regular design, and then I will take this and set another line like here on top of the first one, and then I will use a divide curve for the first and one for the second. So I will have two separate workflows right now. I will have one slider for the first divide curve, like from 1 to 10, and another one for the second curve like this. So I can set a different amount of points in along the two lines. Okay, and then I will try to create a line between these two sets, and I see that something weird is happening, of course. Now I want to make things a little more regular, so I will take the longest list like this. Nothing happens if I repeat last, but if I interpolate, I start to divide the let's say to stretch the list of the first list of points, which has less values, along the longest list. So you see that some kind of balanced and regular design comes from this interpolate behavior. Of course, you have to consider that if you don't set the right amount of data in the two lists, you will always get, for example, in this case, an asymmetrical graphic result. If I have 2 points on top and I have 7 at the bottom, I have this, which is symmetrical. If I have 2 divisions, I have this, which is symmetrical. But if I increase this, for example, to, let's say, 8, so you see that now, for example, this starts to be asymmetrical. Of course, if I add 8 and 8, this becomes like this. If I have 8 and 6, this becomes like this. So you have to find a relationship between the two sets of values in order to create an interesting or relevant graphic result. Okay. Second component of this set of 3 is the shortest list. Now, shortest list is absolutely interesting when you want to regularize your design. Why did I delete this? Okay, this is something that eventually we will use right now. So let's say that we have just 5 points at the top, and we have well, no, in this case it's not that visible, so I will only maintain the last line. So let's go back to our list of points, set multiple points here, like 1, 2, 3, 4, 5, and 6, and then take another point container with multiple points like 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so I want to create a line between these two sets of points. If I do this, we know that Grasshopper is using the longest list. We also know that we can take the longest list component in order to adjust the way that these two sets interact inside the line component, but we want to not to use the longest list as main criterion to define the amount of interactions. Okay, we want to create only connection lines between couples of points. If there is no couple, I don't want any line. Okay, so this means that it's the shortest list that must determine the amount of interactions between the two sets of data. So in this case, we will take the shortest list component, use this to filter the two lists, and if we take a look at what happens in this case, we will have a set of 6 points here, and we will have a set of 10 points here from 0 to 9. Remember that first value is 0. Now what happens when we take the shortest list? What happens is that the longest list, which is this one, is trimmed at the end. It means that after passing the list through the shortest list, Grasshopper will trim the end values. So you see that the last value is 1550, while 17, 19, 21, and 23 are trimmed off from the series. Which means basically that if I do this, I will only be creating the connections between couples of points. We can decide if we want to trim the end, which means we are deleting the last points from the longest list, or we can trim the start, which means we are deleting the first points from the longest list, or we can interpolate, such as deleting 1 point out of X according to the number of points or data that we have in the longest list, just to make it to make this longest list contain the same amount of values as the shortest list. Okay, so once again you can see that there are different behaviors that you can select by right-clicking on the component. Okay, and this is what's explained here in the shortest list section. So you can see that there are these two sets of points, like 4 and 6. This is the trim end, so lines that connect only couples of points in vertical. This is the trim start, eliminating the first 2 points. And this is the interpolate. Okay, so it's very easy. And then there is the cross-reference. Now, cross-reference is something that normally you don't want to do a cross-reference, okay? Especially if you work in let's say, you work in a design process, or you are trying to design something that eventually will go through production phases and so on, because this is something the cross-reference normally generates a result that it's very nice graphically, but it's almost always useless in terms of real world design and objects. Okay, so what happens with the cross-reference? The cross-reference basically in its default configuration, which says holistic, takes all the elements of the first list and makes them interact with all the elements of the second list. So if we take a look at the result directly, you see that there is this kind of interaction between each element and all the elements of the other list. So you see that first point is interacting with all the points of the second list, the second point of the first list is interacting with all the points of the second list, and so on, the third one and the fourth one. Also, you can see it on the other hand, you can see that the first point of the longest list is interacting with all the points of the shortest list, and so on, the second with all the points of the first list, and so on. So it's like everyone with everyone. It's like an orgy of connections here. But let's see how can Grasshopper create this result. I will copy paste these components. I just want to analyze the data sets in this moment. So let's see what we have here. We have 4 and 6 values. Okay, so what happens after the cross-reference? The cross-reference will affect both lists, of course. Okay, so if we take a look at what happens to list A after the cross-reference holistic, we will see that we have 24 values, which is 6 values by 4. So the Grasshopper is actually multiplicating the amount of values. And you will see that there is 24 values inside the list A after the holistic cross-reference. And also, if you go to list B, you will have 24 values for the second list. And these lists are set to have an order that creates exactly the type of connection, the kind of connections that we have just seen in the graphic preview. So I will point it out with lines here in Grasshopper. You see that this is 5, 5, 5, 5, 5, 5, 5, 5, 4 times repeated, okay, because we have 4 points in the first set. So you see that here you have the first 4 items are exactly the 4 points of the shortest list, 5, 7, 9, and 11. And then they repeat. They repeat 1, they repeat 2, and so on, okay? As many times as the amount of points that we have in the second set. So in total, you will have 6 repetition of 4 elements of the shortest list. Here you see that each element of the second list, the longest one, repeats 4 times. So it repeats the amount of times that corresponds to the amount of values in the shortest list. So here Grasshopper is taking the 6 values and multiplying them by 4, exactly like what's happening here, but in the opposite sense. So you see that there is 5, 5, 5, 5, and then 7, 7, 7, 7, and then 9, and so on. So the total number of repetition will be 24 here and 24 here. So Grasshopper can create this kind of interaction, 1 with 1, always. Of course, these 4 lines that we see parallel are converging into the same point, okay? And also, each time that you connect the first value of this set of 4, you are creating 1 connection that converges into the first point of the shortest list. So for example here, and for example here, and so on. So that's why graphically you see this kind of interconnection like this, where this point connects with this, and with this, but also this point connects with this, and this. And then you skip to the second one, 1, 2, 3 connection. This is also connecting with this, and this, and so on. So that's how the cross-reference works in its default setting, which is holistic. Then we have this preview here, and then there is the diagonal. You can see here we will only take a look at the graphic aspect of this change in the settings. But of course, you can always take a couple of panels and see what happens to the repetitions of the values contained into the first 2 sets of points. Okay, so you have diagonal is this one, and coincident is this one. In this case, it doesn't affect the graphic aspect, as you can see. There is no difference between the 2, but you can take a look at the values inside the panels. Lower, which tends to create connection just using the first values of the longest list, and lower strict, and then there is the upper and upper strict. Okay, so you can take a look at the values inside the panels, so just to have an idea of how Grasshopper is setting the repetitions of the data inside the 2 data sets. Okay, so just keep in mind that normally Grasshopper works with the longest list method, and by default this longest list uses the repeat last option in order to create the interactions inside a component receiving 2 data sets in form of 2 lists. Okay, so let's move on and let's take a look at what functions we have inside the list group, starting from exactly the lists functions. Okay, so the first one is insert items. Now insert items is apparently it's very easy to understand what it does, but it has some tricky aspects. For example, I will just point out that when you see this container here with the wireless transmission, it's receiving the standard list that we have created here. So it's a standard list between of 10 values from 0 to 9 with step 1. And this will be used in several analyses during these first sessions. So what we are saying here is that we want to take the list, the original list of values, which is from 0 to 9, and we want to place this item which can be one of these three. Okay, so it can be the first one, the second one, or the third one. So let's start with the easiest one, which is just like asterisk A. Okay, and we want to place this asterisk A with correspondence to the values of, or the position of this list that corresponds to indices 0, 5, and 15. Now, just to point it out, so it's very clear, if we take the original list, you see that this list goes from 0 to 9. Also, the indices goes from 0 to 9. And we want to place this item here in position or index number 15. Okay? And let's see what happens if we do this. We can see that position number 0, index number 0, you see that now you have this asterisk A at position number 0, while the original value of 0 is shifted to position number 1. And then you see that you have index 1, 2, 3, 4, 5, and then you have 6. Now, 6 is asterisk A, while here we said that we wanted asterisk A in position number 5, index number 5. But index number 5 has become index number 6 because we already inserted the asterisk A at the index 0. So we already shifted the list one position ahead. So that's why you see 5 here and 6 here. And then we have 15. And you see that the next asterisk A is inserted in position 17, of course, because the list at this point has been shifted of 2 positions. Because we already inserted the asterisk A in 2 positions. So that's why 15 becomes 17. And as the original list only had values up to index 9 and also the value was 9, you see that now index 9 has become index 11. So it was 10 values of the original list, which are these ones, plus the 2 that we already inserted. So we have index 11, so 12 values, corresponding to value number 9. And then as we want to insert another item, which is another asterisk A, in position number 15, but it becomes 17, you see that there is 12, 13, 14, 15, and 16, which contains null item. Because the original list has no items in that positions, and the item that we want to insert is occupying a position that comes next. So that's why you see these null items here. There is also a wrap option here. If we set it to true, you will see that there is basically a different approach, especially in this case where we are considering an index that is out of range if compared to the original list. The original list indexes range from 0 to 9 as well as the values. So if we set an index to be 15, setting the wrap to true means that instead of going up to value 17, Grasshopper is starting once again from the first index, counting and placing another asterisk A in this case in a new position, which is this one. So you also have to consider, you always have to consider that the indices update when you insert new items in the list. So remember that 15 doesn't mean that you go through the 0 to 9 and then go back. So it would be basically 0 to 9 position number 6 eventually. But in this case, no, because you have to imagine that you already inserted 2 values in the original list. So saying 15 won't get you to value like 6 or 7. It will stay at value 5. Okay. So this is the meaning of wrapping the list. Instead of creating null items to fill the separation, the gap between the last item of the original list and the item that you want to place at index 15 in this case, it will restart from the first index of the list. Okay, so that's wrapping. We'll find the wrap option in several other components later on. I will keep this to false just to have a clearer understanding of what we are doing. And you can, for example, this is the use of panels that we already saw a few minutes ago. This is one single value, asterisk A, which, by the way, of course, it's a text. And here you have asterisk A, asterisk B, and asterisk C, but you see that this is not a multi-line, it's not a multi-line data. Okay, this is just one text. So if I plug this here, you will see that asterisk A, B, and C are being inserted inside one single index. So index 0 is actually containing this thing, which is a text, multi-line text, let's say so, not multi-line data. Okay, and you see that here also in position number 6, which would be 5 plus 1 that we already inserted, is the text, and then you will see null, 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 and ABC in position number 17, which is different from saying I want this multi-line data. If I do this, Grasshopper, as I am trying to insert 3 items in 3 different positions, Grasshopper will insert the first item in the first position, so 0 is asterisk A, and then you see 5 plus 1, which is 6 asterisk B, in this case, the second value, and position 17 you see asterisk C. So this is what happens if you use a multi-line data instead of multi-line text and a multi-line indices list here. So each value, each item is being placed in the correspondent position according to the indices that are coming in here. So that's how insert items work. Then we have the list item. Now list item is somehow easier than that. It just retrieves a specific item from a list of values. We have the classic list from 0 to 9 step 1, which is our standard list for the next hour. And we have basically the list is plugged into the list input, of course. This index says which index you want to retrieve from this list, and it's set to 0, and you always have this wrap component here. So if I take the list from 0 to 9 like this, we can see that value 0 corresponds to index 0 and so on. Okay, so index 0 will output value 0 here in a new list, which is the list of items that we are extracting from our list. Okay, if I change this, I am saying I want index number 7, and index number 7 corresponds to value number 7, and here it is. Wrap is set to false. Okay, so what happens when I say here 9, you will have the value number 9, but when I say 10, this list item start to fail because it will say that index is too high if compared to the amount of values that we have into the list, because highest index is 9 and we are providing 10. But if we switch this wrap to true, 10 will correspond once again to index number 0, and so on. You can see that if we increase this, it will range over and over and over between the same set of indices between 0 and 9. Of course, this is plugging just one index inside the index input, but we can also plug, for example, several indexes like 1, 2, and 3. So 0, 7, 4, it is giving us value 0, value 7, and value 4 in this order. So just remember that when you plug several cables into one single input, for example, the order that you plug the cable will affect the order of the result that you get. So if I plug, for example, 0, 4, and 7, you see that they are exactly in this order. So first one with second one, which has the highest value than the third one, will give us this kind of distribution of values. Of course, even in this case, we can change the values. And if we set this to a higher value than the amount of indices, if we have a wrap set to true, this will keep on ranging between 0 and 9 with repetitions. If this is set to false, this will get angry and will output, or well, worried, not angry, and will output a null value because there is no value corresponding to index number 15. Okay. Then I would go to partition list, for example. This is absolutely important. It's a component, a function that is normally used in several occasions, also when working with data trees, of course, because this is a component that is actually producing, emitting a data tree. So we must analyze this by paying more attention. Partition list, what it does is take a list of values and basically breaks the list into chunks. Okay, and you are not setting the amount of chunks, but you are setting the amount of values that each chunks should contain. Now in this case, for example, I have the standard list from 0 to 1, so from 0 to 9, so 10 values. And I am deciding to divide this list into chunks, each one containing one single element. And of course, as a result, I will get 10 sets, each one containing one value. So 0 goes into the first branch, 1 goes into the second branch, and so on. But if I say I want 2 elements inside one single chunk, like this, I will only get 5 chunks, 5 lists, each one containing 2 values, like this. If I set this to 3, which is basically a non-standard number if compared to the amount of values that we have here, so you will see that the first chunks will contain 3 values and the last chunk will contain the remaining amount of values. So if I use 4, for example, I have 2 plus 1 containing 2. If I use 5, I only have 2 branches. If I start to increase this, I will reach a point when all the values will be contained inside one chunk and there will be no additional chunks. So we are basically obtaining here one single list of values. This, by the way, is affecting also the graphic representation of the cables. Double cable, continuous cable is representing a list of values, while if you have this discontinuous cable, you are seeing a list of lists, basically, which is commonly named as a tree of data. Okay, so this is what happens when you partition a list into chunks. And you can see here the param viewer in both the analytical and graphical representations. So you see that if I set this to 1, I have 10 branches, each containing one value. Here you have 10 branches. You have no idea of the values in this representation. If I increase this to 2, I will have 5 branches, no idea of the values. Here I have 5 branches with 2 values inside each branch, and so on. So that's why I say that param viewer in its analytical representation, analytical aspect, is more important than the graphical representation, because it gives you exactly an idea of what happens inside your data tree structure. But we will discuss the data trees later on in the second session. Okay, so let's skip to easiest tools that we have here in the list set lists group of comments. The reverse list is something that eventually would have very much in a whole bunch of geometry creation tools. For example, just like loft comments and so on. We will give a quick example in a few seconds. So always working with the same list from 0 to 9 with step 1. Reverse list simply reverses the order of the items inside the list. So you see that instead of going from 0 to 9, it's going from 9 to 0. This reverse list is something that you can also apply inside a component, like in this case, for example, this series, which is actually exactly like this one here, is being reversed just inside the output of the component. So here, if you right click, you have the possibility to reverse the list inside the component without using the reverse list component here explicitly. So let's give a quick look at this component in action, or this function in action. So for example, let's say that I'm not going to waste time by drawing freeform curves here in Grasshopper. I'd rather create these curves here in Rhino and eventually have them available in Grasshopper like this. So I want to use these curves to create a loft surface. So I am using a curve component, set multiple curves, and then I will just pick the curves one by one here in this order from left to right. If I plug the curves here in the curves input of the loft, we see that we have this kind of weird behavior. Let's switch to shaded viewport, so shaded preview, so we see what's happening. And now this happens because the curves have opposite directions, of course, but in the loft options we have this aligned section option that keeps the sections aligned without considering their specific orientation. And now we have this loft here, and you see that in Rhino 6, when working with Grasshopper surfaces, there is one feature that disappeared, which is basically a different brightness depending on the phase that we are seeing of a surface. So in Rhino 5 up to Rhino 5 and Grasshopper 0.9, there was the possibility to understand what was the orientation of the surface simply by double checking if the surface was showing this kind of brightness here or not. Now in Rhino 6 and Grasshopper 1, you see that this feature is no longer available. You always see a bright reflection on the surface. So the only thing that we can do here is evaluate the surface in an MD slider 0.5, 0.5. Well, actually we should reparameterize this, but here we have the result. And if I go into display options and adjust the grid so it shows the z-axis, I have no possibility here to get to the okay. Yeah, here we are. So now I see the z-axis, and you see that the z-axis is pointing upward. So it means that the positive phase of this surface is pointing upwards, and this is the negative phase. So this is the only way that we have here in this moment with this evaluate surface. What happens if I reverse the list of curves? You see that the plane is actually switching directions. Okay, so if we do this, we see that there is an effect, a geometrical effect on the construction of our surfaces. Now in this case, for example, you see that, let me for example do like this. If I analyze these curves, you see that this is flipped and this is flipped. So I will analyze only these two here and flip them, so that now we have four curves with the same orientation. I no longer need to align the sections eventually. So you see that everything works just fine. And if we can also reverse here in the input, and you see that now this is the real behavior of the reverse command. In this case, you see that the z-axis has flipped and is pointing downward. So you see also from here it has the same effect. Now this is happening because when you create a loft, for example, let's create a loft in Rhino. If I loft these curves from left to right, I get this result, and if I loft them from right to left, I get this other result. Geometrically we have exactly the same effect, but if we go into shaded mode and then we go into display options, and one setting that I do recommend to all Rhino and Grasshopper users is that you go into the shaded settings, and then you go into the back face settings, and instead of using front face settings, you switch to single color for all back faces, and just pick a color that you would never use as a diffuse color or visualization color for your objects, like for example like some kind of orange or some kind of tan or khaki or whatever. Okay, so from now on, whenever I see a back face of a surface, it will be displayed using this orange color. So let me go, let's go here at the bottom, so I can hit OK. And you see that in this case, for example, I see that one surface gets orange and the other one stays white. And if I go like this, you see that I'm seeing the back face here and the front face here. So changing the order by which you select the curves for a loft, it changes the orientation of the final surface. And that's exactly what's happening here in Grasshopper. If I reverse the order of the curves, I switch from one surface orientation to another one. Okay, so reverse list is something that it becomes useful in this kind of situations, for example. Now let's delete all this example. Let's go back to our explanation here. So reverse list. Sort list is something a little more tricky, and it's a component that is normally used for, well, I wouldn't say advanced application, but yes, it has some kind of tricky behavior. So you should absolutely pay attention to how this component works, because it has several practical applications. So let's place this component here, and let's see what happens, for example, if we try to use it. So it works with two inputs, which are the keys and the values. Keys are numbers that will be sorted using the sort list. Okay, so keys are numbers that gets in the component and comes out from the component in a precise order, from the smallest number to the highest value. Okay, if we have another list with the same amount of components as the keys, or the same amount of items as the keys list, and we want to reorder these elements, these items, with the same, in the same way that the keys would be reordered, then we plug this list into values A, and the output values A will receive the same transformation as the keys. So, for example, if I have a list with numbers from 0 to 5, for example. Okay, so this is basically a list where numbers are already in order. Okay, and then what I want is basically a point container with 6 points. So set multiple points, and then just say I want 1 point here, first point, and then second point, third, fourth, fifth, and sixth. So if I point list this with, let's say, size of 1, so I can see the number, you see that these points are in order like this: 0, 1, 2, 3, 4, 5. Now what I want to do is use here the same order that I see in this sequence of points. So for example, it would be 0, 3, 2, 1, 4, 1, 4, and 5. 0, 3, 2, 1, 4, 5. Okay, so I want this sort list. I want to use sort list to order the points from left to right. So what I want to do is to sort these values here the same way that the keys will be sorted horizontally. So as you can see now, this is giving us an error, because it says we have different lengths for our list, because you see that this panel is actually not a list of objects. We already talked about this, so we must convert this into a multi-line data. So we see that now we have a series of 6 items inside one list, as well as here we have a list of 6 points inside one list. We can also plug these points inside a panel so we can see that we have exactly this same structure, which is very important because the number of keys must be the same as the values that we want to sort. And now what happens after sorting is that this number gets in order from smaller to bigger value. And the same way the points are being sorted using the same transformation that is needed to get from here to here. So if I plug a point container here, and then I use this point list to visualize the number of these points here, you see that now this point list is ordered from 0, 1, 2, 3, 4, 5. So sort list is actually ordering or sorting a list of values that can be whatever type of data you want to sort. Okay, and in order to sort these values here, you use a guide, which are these keys, which are normally a set of numbers that are shuffled somehow with the same way that your original data are shuffled. And then when the sort list reorder these values in a sequence of numbers, then the values will be sorted the same way as the numeric values that we have here. Okay, so that's how the sort list component works. It's very important because it allows to solve very complex modeling situations. Sublist. Sublist is somehow easier than the other ones. It's just take an existing list and gives you the possibility to create a subset of this original list. We already have one default list. Let's grab this wireless component here. So we take this list that remember that it has 10 elements inside with indexes between 0 and 9. Okay, so what we are going to do is define the range of indices that we want to use for the new sublist. Okay, so let's say, for example, that we want a sublist from 2 to 6, and we want this to be a new list. Okay, so 2 to 6, it means we must define a domain, the domain of indices to copy. So we can construct domain here, and we must plug, for example, here a 2, here we use a 6, so domain start, domain end, and we can double check what happens here. We only have values from 2 to 6. Of course, this is a new list, so you see that the indices are set for the new list. They have nothing to do with the original list. Okay, so the list will always start from 0 and with a growing integer number here as the index. But here you can see the values, the items that we are obtaining in this resulting sub list are exactly the elements between index 2 and index 6. Okay. Also, you see that the indices that have been isolated from this original list are exactly from 2 to 6. And now in this case, the value is exactly the same because we see that there is correspondence between the index value and the item value. Okay, so if for example we use this list here and we add 1, and then we plug this here and here, you will see that, and now for example there is a shifting between the index value and the item value. Okay, so you see that the items, the values that are being copied with indices from 2 to 6 are from 3 to 7. Here they are, while the indices that we see here are from indices 2 to 6 exactly, which are the indices which are defined here in the construct domain. So here you see the difference between the two values of the index and the item value. Okay, and there is also the wrapping. Once again, wrapping affects the result if we use a domain that ranges higher than the extension in terms of indices of the original list. Okay, so just in that case, wrap becomes relevant. Okay, so sublist. Now let's go here, replace items. Now replace items is something that you might notice that is somehow similar to insert items. But in this case, he doesn't want to know what values you want to put inside the list. He wants to know what values you want to substitute with values already existing in the list. So replace items. Here it is. Let's go and take once again the standard list that we are using for our examples. And now it says, what's the item that you want to put inside the list? So item is the value or the data that you want to put inside the list instead of the existing values that you can find at these positions, like the indices. Okay, so for example, let's use a text like the item that we want to place inside the list. And remember that we have a list with indices from 0 to 9. We don't want to wrap, so just let's stick to this range for the indices, so 0 to 9. And indices, let's take for example a slider between 0 and 9. So what we expect is to see chow instead of 0 actually. So let's take a panel, let's place it here, and you see that exactly this replace item is working as expected. Of course, if I move this, you see that chow displaces along the list. Okay, and also remember that if I do this is a text, so one single item is being replaced with these two lines. If I do this, like convert this into a multi-line data, like this, let me clearly make it visible here. So you see that now in this index is 3, okay, but we have 2 items here, and so the second one is used to replace the next index. Okay, so if you plug more values, more items here, then indices, they will span from that index to the next one and to the next ones. Okay, so pay attention to this. Normally I would recommend that you pay attention that you have the same number of items and indices that you want to use inside this component, or at least more indices than items, and keep the items like clearly separated. Okay. And also you have wrap that affects the indices that you can use in your component parameters. Okay, so replace items. List length is basically almost useless in terms of it's useless to comment, because you can see that it's pretty straightforward. You have a list. This counts the amount of items that you have in the list. So it's a list from 0 to 9, so it has a number of 10 items inside, and that's it. Shift list is somehow very important. It takes a list and shifts the items inside the list with a shift value. So let's see how it works. We have it here. Let's take our standard list, and this is the list that we want to shift. And what I want to do is, in order to make it clearer, let me grab a panel. Let me visualize these numbers here, and I will use the pen in a while just to understand what happens here. And as a shift value, I will use a value between 0 and 2, for example. And wrap is set to true by default, and I will take a Boolean toggle and leave it to true for now and plug it here, so later on we can just change this Boolean value to false and see what happens. So and let's grab a panel and see what happens with this shift list component. So when shift is 0, we are saying that we don't want to shift the list. Now what's the meaning of shifting the list? The meaning is that here we have item 0 corresponds to index 0, item 1 to index 1, and so on. If we shift the list with shift let's say shift equal 1, which means plus 1, by the way. So it means that this item here will shift position. It will become this one. And this one will go here, and this will go here, and so on. Okay, so basically we will get, with shift plus 1, we will have a list where, let's leave index 0 for now, and then we have 1, 2, 3, 4, 5, 6, 7, and so on. So we are saying that index 1 will contain value 0 because it shifts one position forward. And then we will have 2, we'll have 1, 3, we'll have 2, 3, 4, 5, 6, and so on. What happens when we get to 9? Because 8 will contain 7, 9 will contain 8. But if these values shift one position forward, what happens to 9? 9 would fall out from the list. But as we have wrap set to true, the 9 will be placed in item number 0. So we will have this. I repeat, if wrap is set to true. Okay, so this is shifting one position forward. Of course, if we shift 2 position, this item here will fall here in position 2. And so we will have index 2, value 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 with wrap true. Okay, so this is the meaning of shifting a list. And we can see that, for example, if I shift with 1 or shift with 2, you see that this is exactly what we were describing. Okay, so you see that the items basically are moving one position. Actually, they are moving backward. You see that shifting one position, you see that 1, instead of staying in the index 1, shifts to index 0, and 0 shifts with wrap set to true, shift to position 9. Okay, if I set this to false, you see that elements shift, but the element that falls out from the list simply disappears. There is no number 0 here at the bottom. Okay, so if I increase this, you see that also number 1 disappears. Okay, of course, shift can be an integer value that can also be negative. Okay, so for example, if I take this slider and set it between -2 and +2, now I can also shift on the other side, for example, like this, which is the example that I was showing with the pen. So you see that in this case, 0 goes second position, 1 third, 2 fourth, and so on. And the 9 falls out and go back with wrap set to true in the first position, so index number 0. If I set this to false, 9 disappears. Okay, so that's how shift list works. Now, what can we do with shift list? For example, if I take a line, of course you can, this is just to give a glimpse of the potential that these components have, but you can also imagine more complex situations, of course. So set one line, for example, like this one, and then we already created something similar. I'm going to divide these two curves, but this time I'm going to use one single slider to determine the amount of points. So we will always have a controlled amount of connection. What happens if I shift list a series of points like this? You see that now lines are connecting in diagonal because the points that are here at the bottom, which is the bottom line here, are being shifted one position to the right, or as many positions as we please. So 0 position, they stay exactly the same, but +1, +2, +3, and we have wrap. If I don't want to wrap the list, and so I set it to false, you see that this is what happens. You see that we have less points in the second list. because they are falling out of the original list of points and they are not being kept because wrap is set to false. And this leads us to a problem that we already know, because there are more points here at the top than the points that are here at the bottom. If we only want to connect pairs, couples of points, we can use the shortest list component like this and plug them here. So we avoid these multiple connections, and we can change the number of the shift to as many position as we please. And we can also use this with negative values, -5 to 5. So we have this this behavior here. Of course, if we do this and we are using the shift list, of course we are eliminating the last values using the shift list, and so we have less points in the list B, 5 compared to 9, and so we have only 5 connection between pairs of curves. So everything is clearly understandable in this situation. But for example, shift list is something that you could use for creating I don't know, like diamond patterns, for example, on a facade of a building, just to name one very well-known application. Split list is something that we can also see right here. There is no need of creating examples in this case. We have a set of values from 0 to 9, the standard list that we are using. We want to split the list using a specified index as the splitting value. So you see that when index is set to 0, all the items from that index on will be placed in list B. So basically nothing stays in list A. If this is set to 1, there will be one item, which is the item 0, which will remain in list A, and all the items from index 1 up will be placed in list 2. So remember that here we have, let me grab a second panel. We have this situation here. So I'm saying that I want to split the list here. So from index 1, all these values will fall into list B, while before this value, which is set from this layer here, before this value, all the items will be placed here. And so if I increase this value here, you see that more items will be stored in list A and less in list B, of course. Okay. Just remember that this slider here, this index, states from which index we want to place the items into list B, included. Okay, so that's how split list works. And this patch, which is quite a common command in Grasshopper workflow, it allows to take a list of values and dispatch them into two lists using a dispatch pattern, which is basically a set of Boolean values, true, false. Maybe you don't know it, but in Grasshopper, Boolean values like true, false can also be set by integer values 0 and 1. Actually, they are just some logic values: true, false, on, off, 1, 0, and so on. So if we take, for example, an integer container and we pass these values to the integer container, you see that we get no error here. And if we take a look at the content of this panel, you see that it's set to 1010, which is true, false, true, false. And if we pass the value from this integer container to dispatch pattern, you see that nothing happens because it recognizes the true, false pattern even using the integer values. Okay, so I'm going to disconnect this, Control Shift these cables, and go back to the original definition. So what happens here is that we have our standard list from 0 to 9, and we have this pattern, dispatch pattern, which says true, false, true, false. Of course, we have more items here. They are 10 in the list and 4 in dispatch pattern, but this is not an interaction like the ones that we have seen previously in other components, like lines between 2 points. In this case, the pattern, if it doesn't cover the whole amount of items that are getting in the list input, this pattern will simply repeat until it covers all the length of the list that is coming in the list input. For example, here we have true, false, and Grasshopper would repeat once again true, false, true, false, true, false until it covers the length of 10 items of the first list. So basically we can also take this. It has the same effect. As you can see, there is no change if we also plug the other two true, false. And we can also, how the dispatch works is that it builds this pattern of true falses here, which are basically 5 couples of true false in this case, because we have 10 elements here, we need 10 true falses in the dispatch pattern. And what it says is if the item is basically paired to a true, then it will be sent to list A. If the item corresponds to a false, it will be sent to list B. And so you can see that true will correspond to the first, third, fifth, and so on. And you can see that 0, 2, 4, 6, and 8 go into list A because they correspond to a true. While 1, 3, 5, 7, 9 go into list B because they correspond to a false. Okay, so that's how the dispatch pattern works. And of course, if we change the pattern, we change the way that objects are or items are distributed between list A and list B. If everything is set to true, all the items will go to list A. If everything is set to false, all the items will fall into list B. Okay, but this is pretty obvious. Null item. Now, null item is it's very important. It's also a common function that is used in several applications, especially if you want to, for example, clean data sets. You might want to use a null item, like exactly how we are going to do right now. For example, we have this list. This list comes from a previous example. It was the insert items with Boolean toggle set to false. So we saw that in order to cover the index number 15, a bunch of new indices were added with a null value because there was no original value in the original list, and there is no value set in the position of 12, 13, 14, 15, and 16. So we have this list which contains 5 null items. And let's go here. This is the list actually. And this null item, what it does is take the item and understand if it is null or not. So null flags are basically true, false. False if the object is not null, and true if the object is null. So you see that we have 5 nulls here from 12 to 16, which are exactly the null values in our original list in this case. Invalid flags are basically also detecting if you have invalid items in your list, and description is why this object or this item is being flagged as a null flag or invalid object. So you see that in case of null object, data does not exist in position 12, 13, 14, 15, and 16. This is the explanation basically. Now what can we do with this null item is that we can, for example, eliminate the null item here from this list and clean the list from invalid or null items by using, for example, a dispatch pattern. So if I take this and take the list, the original list, and use this null flag as dispatch pattern, and then take a panel and plug it here. So you see that here we have the 5 null. Why do we have the null in list A? Because null item gives us true when it detects null items. And so this dispatch pattern has true, which corresponds to the null item that will be sent to list A. While in list B, we have the valid values without the null items. So we can use this null item to clean data sets from null items or invalid data. Okay. And then last row for our set list group of components, replace nulls. You see that this is something that eventually might appear somehow like the operation that we just described, but it's not like that. This gives us the possibility to substitute to replace the null items with another value. Okay, so you see that it corresponds to the null item here. We have a asterisk good, which is this text that I placed in the replacements here. So it gives us the let's say correct list in this case, where we no longer have null items, and it also tells us how many replacements were performed inside our original list. So you see that count is set to 5 because 5 items were replaced by the replacement value here. These two here are very important component. They allow to basically pick data from various data sets according to a defined order. Now, they work in a different way. They might look like identical, but they're not. They both work with a pattern. They both accept several data streams. So if you get closer, you see that you can add data streams to both of them. I left this with an additional data stream which remains void. I will show why in a moment. So basically, each data stream receives a number. So you see that these numbers here is plugged into data stream 0, letters are plugged into data stream 1, and 2 is void. And then I decide here what pattern do I want to use in order to grab values from these data streams. So if I say 0, 0, 1, 0, it means I want to take one value from data stream 0, another value from data stream 0, a value from data stream 1, a value from data stream 0. If I don't write any 2 here, there is no need. There is no need for this component for this function to read the 2 data stream. Okay, and you can see that if I say 0, 0, 1, 0, what happens is not that I read data stream 0 twice, so I get 1 and 2, and then I read the data stream 1 just once, but I don't get letter A, I get letter C. Okay, because I am using this one which corresponds to the index number 2. So I read data stream 1 in position given by this index here. So that's how this new list is built, basically. If I say I want to read 2 here, you see that this becomes orange and a null value appears because there is nothing coming in here inside the 2 data stream. Okay, so just pay attention that you just only use data streams or visualize data streams if you are going to populate them with some value. Okay, so I'm going to, normally I would recommend that you eliminate this in order to avoid misunderstandings or error. I will leave this in this definition because it will be shared as course material. Basically Weave does something very similar. Okay, so we always have data streams. In this case I avoid placing the data stream number 2. We have a pattern that decides what do we want to pick, what values we want to pick. You see that in this case, for example, we have 0, 0, 1, 0. And so we have here a list that says 1, 2, which is expected. Then there is 1 that says read a value from data stream 1, and this time you see that A appears. And then there is 0 once again, so 3 appears because 3 has not been read from the first 2 zeros. So basically Weave is merging or is blending, more than merging, is blending the 2 data sets according to this pattern, and this pattern repeats. So it would look something like 0, 0, 1, 0, 0, 0, 1, 0, and so on. Imagine that it repeats. So in this case, for example, what happens is that Weave must complete all the sequence of these 2 data streams. So you see that it has 0, 0, 1, 0, so it has 1, 2, A, 3, which is this one. Then we have 4, B, C, D. Why do we have 4, B, C, D? Because after reading imagine that this is repeating. Let me visualize this with a pen. So it repeats 0, 0, 1, and 0. So once it completes the first set, for example, this means 1, this means 2, this means A, and this means 3. Okay? And then it repeats. So 0 means, once again, read from data stream 0. The next value will be 4. So it is 4. And when it says 0, the first data stream is already over. There are no more values here. And so the only thing that this weave can do is start reading, even if this says 0, start reading from the remaining values, which are all the values from the data stream number 1 that have not been inserted into the new list. So it says B, C, D. Okay, so it's a completely different way of working for this component, for this weave, with respect to the pick and choose. So pick and choose allows to select not only from which data stream you want to collect the numbers or the values, the items, but also how many values you want to collect inside your new list. Here, no, you have a pattern that simply blends the two data sets together using all the items belonging to the two data sets and picking them according to this pattern. Okay. And now the last two components that are here in this subgroup: combine data and sift patterns. Of course, one thing I must say, probably, or well, I'm quite sure that you will never be using all these components in your standard Grasshopper workflow. Okay, but it's important to understand what these components do, because in case you miss something, you might remember that, oh, there was that component, so maybe it will be useful. So, for example, one thing that Grasshopper users tend to ignore is the sets group of components that we will be exploring later on, which is absolutely fundamental for many applications in Grasshopper. We have the once again the list containing null items here in our initial workflow, and you see that here, for example, combine data. It's a component that takes two data streams and creates a new set, a new list, using only non-null items. Okay, so that's why I used a reverse list, because this way I get two lists with a different set of values. Well, actually the values are the same, they are sorted differently. With null items in different positions, basically. So this has null items from index 12 to index 16, and this has null items from index 1 to index 5. Okay. So as a result, let me leave it like this. So combine data, what it's doing is saying, okay, let's see from data stream 0 to 1 if we have a null item here in list number 1, I will use the other one. But there is no null item here, so it is actually creating this item from the first list. Then it comes the index from 1 to 5, where the first list is non-null and the second list is null. So values here are taken from the first list. And then we get to the list, to the values number 12, 16, which are null in the first list and non-null in the second list. And so you see that this component takes the non-null values from the second list, 43210 here. And then once again, the first list is non-null, and then you see asterisk C. Okay, so it's just taking this these two sets of values and then taking only the non-null values. Of course, you can also add data streams and blend more data sets together using this logic. And you can see that here you have a mapping in the index output. You have a mapping of what data stream has been picked in order to consider non-null items. So you see that it's from index 0 to 11 because list 1 is non-null from 0 to 11. And then you have this 1, 1, 1, 1, 1 because list 2 is non-null from 12 to 16. And then once again, data stream 0 because data stream 0 is non-null in position 17. Okay, so that's how this combined data works. And finally, the sift pattern. Sift pattern is basically uses a pattern to sift means like filter or yeah, more or less filter values. Okay, so basically we have a list of items like the standard list with null items, and then we are saying we want to sift or filter these panels, these items, using this sift pattern here. And so you see that, for example, here we have two outputs here. Okay, so we are deciding basically where do we want to send the values from this set. We can also get closer here. This is a dynamic component, so we can add several outputs here instead of inputs, of course. So if we add one, we would have 2, and we can also use 2 as the sift pattern. And so we can filter these values by sending them into, for example, 0, 0. It means take these two values and send them to output 0, like this. And then you see that there is 1, which sends the index number 2 to output 1. And then there is 0 once again, so it means that list index number 3 will be sent to output 0. And then you see that this pattern repeats, 0, 0, 1, 0. Okay, so let me grab the pen. You see that this is basically 0, 0, 1 is null because it is sent to the other list, and then there is 0. And then we have 0, 0, 1, 0. And then 0, 0, 1, 0. So each time you have 1, you see that it is null because here 0, 0 is null, 1 is non-null, and then 0. And then 0, 0, 1, 0, 0, 0, 1, 0, and so on. Okay, so it's like somehow we can think about this sift pattern like a dispatch, more or less, because if you think about 0 and 1 like true, false, in this moment we are saying false, false, true, false, which would send exactly with the dispatch pattern these values into list A or list B. But in this case, we are creating a list with the exact same amount of items as the original list, both in output 0 and in output 1, by including null items where the item is being sent to the other list, basically. And also we can take this and create a third output, and say, for example, I want 2 like here, and so we will have another output with 1 value out of 5 that's being sent to list number 2. So you see 1, 2, 3, 4, and 5th value. 1, 2, 3, 4, and 5th value is here. And then you see that there is nothing here because basically let's do it like this, because basically the next 2 corresponds to a null. So we can double check this. It is 0, 0, 1, 0, 2. So it is, this is being sent to the other list. So then 0, 0, 1, 0, 2. So this is sent to the third list. So 0, 0, 1, 0, 2, it takes the null values. And then 0, 0, 1, there is no time to get back to 2 once again. So we will have 3, 7, and null, 3, 7, and 1, 2, 3, 4, 5 null, and all the rest is null because these values are sent to list number 0 and list number 1. So it's a little more powerful than a dispatch because you can also create a more controlled shift pattern in this case. Okay, so this is basically it for the list group of comments. Let's control E these, because even if they are just a bunch of numeric components here working, so it's not time consuming, but there are plenty of them, so it's always better to deactivate the components if you are not using them in order not to stress the computer. So let's move to the sequence group of commands. This is somehow easier than the previous one. It's just pure understanding of what these components do. There are some of them which are very important and very useful, and actually they are quite common in a standard workflow. So let's go and see what we have here. Let me activate this second set here. Of course, we will be working with a series of values, but in this case, we have 100 elements here, 100 items from 0 to 91, to 99, sorry. And this is the list that we will be using in this second block of components. So take the list and start with the first component here, which is call index. So call index, what it does is remove elements from the original list according to the index that you want to use. So for example, now I am using two indices, 0 and 0, which are equal, basically identical. So what I'm doing is eliminating twice, which is not possible. It can be eliminated just once, of course. So I am eliminating the item that corresponds to index number 0. And you see that, for example, we have 100 values coming in and 99 values coming out from this list. And you can see that the list was actually starting from 0, which had index number 0, and now the index number 0 corresponds to item number 1. So you see that the item 0 is being eliminated by the call index. And of course, if I decide to eliminate, for example, 0 and 1, you see that also number 1 disappears. And if I eliminate, for example, like 0 and 8, you see that item 8 has disappeared, as well as item 0. So you can decide what item you want to eliminate by specifying the index of the desired item. And of course, wrap means that if you exceed the amount of the number of indices which is present in the original list, then the wrap will basically start back and start counting back from index number 0 in order to understand what index you want to eliminate. Normally, in this case, I would not recommend to work with wrapping, because it's very difficult to understand what item I am removing if I don't use exactly the index value that I see in the original list. Okay, so I would not recommend to use wrap, or rather wrap is set to true by default, but I would not recommend to use a index value which is higher than the higher index that you find in the original list. Call nth. This is very interesting, because it takes a list and eliminates the one item out of this value. So for example, you see that it's called call frequency. So if I copy paste this panel and see the original list here, you see that it is 0, 1, 2, 3, 4, 5, and so on. I am setting call frequency to 2. So you see that 0 is kept, but then 1 goes away and 2 is kept. 3 goes away and 4 is kept. So one value out of 2 is maintained in the result. Okay. If I cannot set this to 1 or 0, because as this call nth will just get angry, it gets red, of course, because if I decide to eliminate with a call frequency of 1, all the values will be eliminated. So this component will not give any result. So that's why the call frequency must be at least 2. And if I increase this, you see that 3, for example, only 0, 1, 3, 4, 6, so one value out of 3. So 0, 1 are kept. The third one is 2, goes away. 1, 2, 3, 5 goes away. 1, 2, 3, 8 goes away, and so on. So if I increase this 4, 0, 1, 2, 3, 4, so you see that 3 is the fourth value and goes away, and so on. 1, 2, 3, 4, 7 goes away, and so on. So call nth basically determines allows to eliminate values from items from a list with a predetermined frequency. Call pattern is like basically it's a substitute for dispatch pattern, especially if you don't want to work with two sets of data coming from the dispatch pattern. The call pattern has the same behavior, but it only keeps the values that corresponds to the pattern that we are using. For example, here we see that we have our original list of values from 0 to 99 in order, in sequence, and we are saying call pattern is set to true, true, false, false. And so you see that 0 and 1, which are the first two values, correspond to true, so they are kept by the call pattern. While when the call pattern is false, the correspondent values are eliminated. So you see that there are no 2 and 3. Okay, and then 4, 5, 6, 7 go away, and so on. So if I set everything to true, all the values are being kept. If I say false, true, 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 0 goes away, 4 goes away, 8 goes away, and so on. If I false, false, true, true, 0 and 1 go away, 4 and 5, 8 and 9, and so on. So I can change this pattern to whatever I want. So for example, in this case, true, false, false, true, which is basically a true, true, false, false, but with a shifting. Okay, so you see that 0, 1 and 2 go away, 3, and then 4, 5 and 6 go away, and then 7. So it's like having 3, 4, 5, 6 go away, 6, 7, 8, 9, 10 go away, 11, 12, and so on. So it's 2 yes, 2 no, basically, but with a shift with respect to the actual true, true, false, false. Call pattern. Okay, so basically they are very, very similar, the call pattern with the displays with the dispatch pattern. We can also do this. If I go here and copy paste this, like yes, let me double check. Yes, let me grab the dispatch pattern. So basically what I want to show you is that if I take the same list and use the same dispatch pattern here, and I take list A, you see that call pattern is actually removing or keeping 2 values out of 4. Okay, so we have 0, 1, 4, 5, 8, 9. So if I go here, list A, I have exactly the same values, while in list B I have the eliminated values. Okay, so dispatch pattern and call pattern works exactly the same, but dispatch keeps the values that are being called by the call pattern in a separate list, which is list B. So it depends. If you need to have access to the values that are eliminated by the call pattern, then use the dispatch, and if you don't need this double list, then you just use the call pattern. Dispatch and call are normally used, for example, in all the definitions of attractors, for example. Call pattern. Random reduce is a component that takes a list of values, a data set, and then gives you the possibility to reduce the amount of items by determining the reduction factor. So if it's set to 0, then no value will be eliminated by the original list. So we have 100 values going in and 100 values coming out from these random reduce. But if we decide to eliminate values, like eliminate 80 values from this list, you see that 100 go in and 20 come out from this component. Which one? Well, it's random. Okay, so this is the random part. So you see that these are 20 random values kept by the random reduce. So we decide how many values we want to eliminate, and the seed, as in all the random functions in Grasshopper, allows to determine which 20 values are being kept, or which 80 values are being eliminated by this random reduce. So if I change this, I will always get 80 values eliminated. I will always have 80 values eliminated from the original list, but in a different order. So the survival will be 20 different numbers each time I change this value here. Char sequence. Char sequence is basically a sequence of character generator. So you decide how many items you want in the sequence. You decide the char pool, which can be a custom char pool, as you can see, and you decide the format, which is optional. It allows to determine the formatting mask. Now, don't think about formatting mask as formatting a text. This is something a little more complex, and we don't want to go into this. It is normally never used. Basically, it has to do with the string formatting and not with the text formatting. So we won't go. We won't cover this thing. We will also find this thing in another occasion later on. I don't remember when, but I will point it out. So in this case, I want to create a sequence of 127 items using this char pool, which is 1, 2, 3, 4, 5, 6, 7. Char pool is a text, is a string. Okay, so it's not a list. It's not a list of values. Okay, it's just one single set of characters. In this case, numbers from 1 to 7. And you see that it starts to create this sequence like 1, 2, 3, 4, 5, and these are only 7 numbers. I want to create 127 items from these 7. So if we take a look at what happens after number 7, you see that this happens. This is not 11, 12, 13. This is basically taking character number 1, take it as a fixed value here, and starting repeating the whole set of characters here once again. So this is 1, 1, 1, 2, 1, 3, 1, 4, up to 1, 7, and then we have 2, 1, 2, 2, 2, 3, 2, 4, and so on. This allows to create a series of value which will never be repeating actually. So you see that when you get value 7 with a repetition of 7, 1, 7, 2, 3, 4, 5, 6, 7, then you start again from 1, but 1, 1 is already present. So it becomes 1, 1, 1. So you have 1, 1, 1, 1, 1, 2, and so on. So this allows creating a set of 127 values which are never repeating, a sequence of values that never repeat. If we count the amount of items in this sequence, you see that they are exactly the same amount of the count set here. If you don't use any custom char pool, normally this works with a standard char pool, which is the whole English alphabet. Okay, so you see 26 characters here, and you will have this sequence A, B, C, D, E, F, G up to Z, and then you will have A, A, B, A, C. This makes it more evident that than if you work with numbers that it is not 11, 12, or 37, or 41. Is this 3, 7, 4, 1, 4, 2, and so on. It is the repetition of one character and the whole series of the existing characters. I don't know if it's better to go down here or to the right. Maybe let's follow this order here. So I will go down here, duplicate data. Duplicate data is basically a component that allows to repeat data as many times as you want, in order or not. So the data that we want to duplicate are A, B, C, D, E. It's a list of items. In this case, it's not like the char pool. The char pool is something unique. Normally, you will never find a set of characters, for example, or items in general in one single line, because this is actually a text for Grasshopper. But in this case, this component is capable of interpreting these as separated items that can be used in this particular way. Okay, but normally this is not a standard application in Grasshopper. So this is normal. Like I have 5 items in one list, so it's a multi-line data set. And then I take this data and I want to repeat all these values here 2 times and keep them in order. Keep them in order, it means that they will be repeated like this: A, B, C, D, E, and then A, B, C, D, E, and so on. If I increase this to 3, I will have 3 repetition of the whole set, but always like this: A, B, C, D, E, A, B, C, D, E, A, B, C, D, E. While if I say I don't want to keep them in the same order, they will be repeated 3 times, but 3 times value A, 3 times value B, 3 times value C, and so on. Okay, so it's like repeating them, but with a different logic according to the Boolean toggle that is connected to order. Okay, so this is duplicating data. Then there is Fibonacci, which is a Fibonacci series generator. It's pretty straightforward. If you want to play with it, I won't go through a detailed explanation because it's absolutely useless. Then there is the range. Now the range is it's absolutely important, and I'm going to describe it in a separate explanation because it's something that you will find very often in your workflow, and it is used in many applications. Now, the range is one of those components that when you place them into the canvas, it is set to work with a default domain of between 0 and 1. Now, this domain 0, 1 is the so-called normalized domain, and Grasshopper in many occasions work with this normalized range or normalized domain 0 to 1. Especially when you are working with the parametric representation of curves, surfaces, and so on. So that's why the range normally has this 0 to 1 domain set by default, and steps is set to 10. So what does it mean? It means that you can take a range and divide it into several steps. Now, just so that you understand what's the relationship between steps and the values that are output by the range, if we take a range, for example, between 0 and 1, this range is actually one single step. So if we set steps to 1, what we will have here would be 2 values, 0 and 1. So when we give steps a value of 1, we will have 2 values as an output. If we divide the range 0 to 1 into 2 steps, like this and this, we will have, as a result, 3 values, 0, 0, 5, and 1. If we divide it into 4 steps, we will have 0, 0, 0.25, 0.5, 0.75, and 1. So 4 steps means 5 values. And on and on. If you think about it, 1 gives us 2 values, 2 gives us 3, 3 of course gives us 4, and so on. So the number of values that we get here from the range component is 1 more than the steps that we specify here as the input. Okay, so if I take, for example, a slider between 1 and 10, we cannot divide a range or something by 0, of course, so steps as a lower limit of 1. Then let's see what happens here as a result. We only have 2 values, which are the extremes of the domain, of course. If I set this to 2, we have 0, 0, 5, 1. So steps 2 means 3 values from the range. And so on. We have 3, 4 values, 4, 5 values, and so on. So 10 means dividing the domain into 10 steps, 10 parts. And then we have 11 values from 0 to 1, passing through 0, 1, 0, 2, 0, 3, and so on. Okay. So this is how the range works. Of course, we are working with the normalized domain, but we can also construct a domain just remember that when you want to parameterize this domain here, if you want to maintain 0 as the domain start, there is no need to construct the domain. You can also take a slider between, I don't know, 0 and 100, for example, and plug it here. If you plug one single number into a domain, the domain will assume that the start value will be set to 0, and the domain end will be set to the value of the slider. So saying 0 means that I want to create a domain between 0 and 0. But if I increase this, I am creating a domain between 0 and this value. Okay? So if I set this to 1, I am always saying domain set to 0 to 1. If I say, for example, 50, I am saying domain 0 to 50. If I want to parameterize also the domain start, I must use the construct domain. So for example, if I plug this value here and I copy here in the domain start and use this, now I'm using a domain between 50 and 50. So in this range, any value that I want to get from the range will be 50. But if I decrease this, now I have values between 45.087 to 50, 11 values in this range. Okay, and so we can parameterize this range in whatever we want. So this is how the range component works. It is very, very useful, especially when working with things like a graph mapper. Normally, this is one of the situations where you might want to work with a normalized domain, because the graph mapper only accepts, or by default accepts, values between 0 and 1 and outputs value between 0 and 1. You might know, or someone might have told you that you can double click here and you can change the range both in X and Y. So basically adapt the graph mapper to whatever range that you want of values that you want to plug into the graph mapper or get from the graph mapper. But I would recommend that you never change these values here and do some data manipulation in order for this graph mapper to receive values from 0 to 1, and then manipulate the output if you want a different set of values. Okay, just try to avoid manipulating the graph mapper, because else you might let's say get some undesired consequences. So in this case, for example, I am getting values between 0 and 1 with a step of 0, 1. So you see all the red lines here. These red lines, by the way, appear only when they are not too dense. So for example, if I set this slider to 110, you see that as I increase this, these red lines start to faint, because they will become very dense, and the graph would be basically a red stain inside the canvas. So that's why they tend to disappear as you increase the number of steps. And then here you have these values from 0 and 1, and this is basically the sinus distribution of values between 0 and 1, of 11 values between 0 and 1. So you see that there is a different growth of the values between 0 and 1 with respect to this, which is linear. Okay, so this is one very useful and common application of the normalized domain range. And then repeat data. Repeat data, this might sound a little confusing, because we already saw the duplicate data here. Repeat data works in a different way. It takes a list of values of items and repeats them until it gets to a total length for the new list set by the length slider or length input. So what happens is that I don't have a precise number of repetitions of these values here. I repeat them until I get to this number of items. Okay, so for example, in duplicate data, if I set this to 1, I will have 5 items in the output list. If I set this to 2, I will have 10 values, 15 values, 20 values, and so on. Okay, while in this case, if I have 5 items and I want a new list where these values will be repeated until we get to 6 values, then we will have A, B, C, D, E, and A, because only A needs to be repeated in order to get to 6 items, and so on. Okay, so it's somehow different from duplicate data. Okay, so let's take a look at this, the last sequence comments here. You see this comment here is called actually sequence. It allows to generate a custom series sequence of values according to operations that we can perform in on existing values in the series. It's like the Fibonacci series, for example. Fibonacci series works so that, for example, it starts with 0, then there is 1, and then the third number is the addition of the first and the second one. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on. Okay. So sequence allows to create this kind of number sequence, but with a custom pattern. Like, for example, in this case, we have n minus 1 plus n minus 1 in this panel, which is not connected. By default, this says n minus 1 plus n minus 2, which is actually the Fibonacci series. So, for example, you see that in this case, if I change the initial values to 0 and 1, we get exactly the Fibonacci series, which is identical to this one. Okay, so Fibonacci series, the notation says n minus 1, which is, if we are talking about the third index here, which is this value here, we will have n minus 1 plus n minus 2. So n minus 1 is this one plus n minus 2, which is this one. So we get 1, and so on. So if we change, for example, the notation, we can create custom series like n minus 1 plus n minus 1. It means that each time you switch to the next index, then you will have 2 times the previous value. So in this case, you see that you have starting values here are 0 and 1, and then we have 2, which is 1 plus 1, and then 4, which is 2 plus 2, and so on. So this is some kind of geometric progression eventually. So you see now here we have the amount of values that we want in our sequence. So it's pretty simple. I have never used it in real life scenarios, but it might be interesting to experiment with this kind of notation here to create custom series of numbers. Then there is the series. We already know the series because we have been using it since the beginning of this course. It's very simple. It's just create a series of number, a progressive series of number, starting from the start value with a fixed step, which is the increasing that we get between two subsequent values here, and the number of values that we want to generate in this series. So if I change, for example, the starting value to 1, as step is 0, then nothing will be added to the next to create the next value. So we get a list of 1. If I increase this to 1, we will have a classic series of 1, 2, 3, 4, 5, and so on. If I change this back to 0, you see that we have the standard series, which is 0, 1, 10. Of course, I am only working now with integer values, but actually these values can also be floating point numbers, not the count, of course. I cannot create 7.32 values in one series. It's either 7 or 8. And so we can change, for example, these values to whatever we want, and we get a series of values with starting with this one and with a step increment of this value here. And we can change the amount of values in our series. Then there is stack data. You see, always working with our letters here, A, B, C, D. You see that stack says 1, 2, 3, 4. Now, you must provide as the stacking pattern a list of numbers, of integer numbers, which is basically the same length of the data to stack length. Okay, so for example, we have 4 letters with these 4 items stacking pattern. So the stacking pattern say I want 1 repetition of A, 2 repetitions of B, 3 repetitions of C, and 4 repetitions of D. This is what the stack data does. And last but not least for this sequence analysis is the random function. The first 2 random functions that we see, well, actually no, because we already saw the random reduce component. So random reduce, jitter, and random are the three basic random functions in Grasshopper. I already said this, but random in Grasshopper is not actually real random. It's just like a pseudo-random. Let's first take a look at the random values generator, which is this one with this fancy icon here. So random is basically, let me unplug this domain here. Random is normally creating a number, one single random number in the normalized range between 0 and 1 with a seed that, if I am not wrong, yeah, exactly, is by default is 2. Okay, and the random function produces this kind of value here, 0.771094. This is the random value that you get whenever you place a random component in your canvas. So for example, if I drag another one here and plug it here, you see that it's emitting exactly this value. Okay. So if this was a real random function, and you can try it, if you take the random component and analyze the output, you will find exactly this value here. So if this was a real random function, you wouldn't get exactly the same value that I'm getting here. Okay, and also if I change the seed, for example, to 10, I get another value. But if I change back to 2, I go back to exactly the same value as before. So this is not a real random number generator. It all depends on the seed. So the seed is actually the parameter that defines the distribution of random numbers inside this range domain here. So I can also create a sequence of values here. You see 77, 40, 16. I can change this, but if I go back to 2, I go back to this exact same list of values. Okay. So normally the random generator has this default range, which is set to 0 to 1, the normalized range. But you can also customize this range with a construct domain, for example. So now our 3 random values are being picked inside this domain between 0 and 20. But of course, we can change it according to our needs, and also we can shuffle the values inside this domain. Well, not exactly shuffling, but extracting 3 different sets for each seed that we change here. And then there is the jitter. Jitter is another random component. It doesn't create values, it just shuffles the values that we plug into the list input. So we have here a list between 5 and 14, and we have the jitter component, which is outputting exactly the same list because jitter factor is set to 0. So if I increase this, we see that slowly values start to shuffle. Of course, if I set this to 1, I have complete shuffling of the values. Okay, so normally jitter has jitter factor set to 1 because eventually we want to alter the order of the original list. So that's why jitter is set to 1. And then we have seed. So each time we change the seed, we see a different variation, different shuffling of the original values happens. And you see, for example, here in this indices, you have an idea of the remapping that occurred while jittering these values. Okay, so for example, you see that now item 0 says 9 because it is saying that the numbers item 0 in the new list, which is 14, corresponds to index 9 of the original list. Okay, so you see that 1 says 4, and if you go here, index 1 corresponds to 9, and 9 corresponds to index 4 of the original list, and so on. Okay, so you have a mapping of the changes that occur during the jittering of your original list. And so this is the analysis of our sequence group of commands, which is this one. And now let's turn this completely off by Control E, and let's take a look at this sets group of components. Now sets is something that that it's absolutely useful when working with Grasshopper. This group of commands allow to create a series of useful operations with sets of data. Now let's see what this component do. So let's take, for example, a couple of series, and these series are absolutely identical. They are two standard series between 0 and 9 and between 0 and 9. And you see that if we plug this series together into one panel, we can see that the first series occupies the first 10 position, and then the second series occupies the second 10 positions. Okay, so we have 0 to 9 and 0 to 9 once again. Now what we want to do is create a set, which is the first command. And it says, it's important to understand the meaning of these words. It says it creates the valid set from a list of items. And it says that the valid set only contains distinct elements. So in our case, for example, our set contains duplicated elements because they all repeat once. Okay, so we plug this list here, and we see that the set is actually containing 10 values between 0 and 9. Okay, so we see that, for example, here we have a list length of 20, and here we are back to a list length of 10. So basically this create set is actually removing duplicated elements from an existing list. So even if the name is create set, this can be useful when you have duplicated elements and you want to get rid of them, because you only want one single repetition of one specific data. So if you see that list, for example, is not asking for a list of numbers, it's asking for a list of data. So for example, say you have I don't know, duplicated points in a set of data. Then in this case you can create a set by eliminating the redundant values. So let's take let's give it a try. So I will take a point component and I will set one point here. So I have this one, and I will repeat data. We already know this from the previous analysis, and I want to get to a length of 5. So now if we take a look at this, we will have 5 repetitions of the same point, and I want to create a set using this, and here we have just one single point. So duplicated points have been removed. Now there is also one observation about this. We have to double check if this actually works, because in Grasshopper there are two ways of handling data, and they are basically based on coordinates. In case, for example, you might want to analyze the coordinates. You see that we have one single point which is -10, 1, 0. And here we have 5 points all with -10, 1, 0. And then we go back to a set of one single point, -10, 1, 0. So this is obvious if we are talking about coordinates. Okay, so if create set is able to detect the coordinates of the points and just eliminate the duplicated data, then everything is just fine. But we have to double check that create set is capable. It's also capable of working with different objects, not just repetition of one object, which is something that is not that obvious sometimes. So if I take this point here and I take it and move it, just let's do some stupid things. So I move this and then I move it back with a -x. So actually what I'm doing, I'm moving this point, the original point, up by a 10 motion factor, and then I'm moving it down by -10. So this is actually the same point with the same coordinates, okay? But in Grasshopper this is a different point because it comes from another workflow, okay? So it's not exactly the same point. And then I will take this and plug it with a shift here. So now we have 5 repetitions of 2 different points in terms of object ID, for example. So here we have 5 objects coming in, and here we have 1 single object coming out. So this create set is very useful because it can detect duplicated points or duplicated data inside one single set. Just remember that when you see here, for example, this is the right time to comment this. If you say that one input is telling you list as list, it means that if you plug here a set of data, the analysis will be performed inside each list. So here we are plugging one single list, so the create set will work on the whole set of data inside this list. But if you plug a tree here, as we will see in the next session, if you plug a tree, then this create set will work inside each branch of the tree. Okay, so just remember this when you see an input that says give me values as list. If you want to create to have this component running over all the data that is coming in independently from the data structure, then eventually you might want to flatten this. We will talk about this later on, but just keep in mind that many components in Grasshopper specify that they want data as list. Okay, so this create set is very important as a Grasshopper standard function. And then set difference, you see that it takes 2 sets, of course, and then creates one set where using the elements that are present in set A but are not present in set B. So it's a difference between the first set and the second set. So I just changed the starting value of these 2 series. So the first one starts from 0 and the second one starts from 5. And it's evident that items from 5 to 9 are repeated in the second list. Okay, so the difference takes only the values that are contained in list in set A, but are not contained in set B. So it's basically deleting the 5, 6, 7, 8, and 9 from list A, from set A. Okay. As you can see, the remaining values 10, 11, 12, 13, and 14 are not even taken into account in this operation because this difference starts with the first series from 0 to 9. Okay. Then set difference. This is a symmetric difference actually. So difference S means symmetric difference. This takes all the elements that are present in set A or in set B, but not the elements that are present in both series. In this case, in both sets. So we have the first list from 0 to 1, the second list from 5 to 14, and we see that the set difference symmetric is 0 to 4, which are the elements contained into set A but not in set B, and then 10 to 14, which are the elements contained in set B but not in set A. So elements 5, 6, 7, 8, and 9 just go away because they are duplicated inside the 2 sets. Set intersection is actually the inverse of the set difference. You see that it only keeps the elements that are shared by the 2 sets. So you see it's 0 to 9 and 5 to 14. Between 5 and 9, all these items are shared. They are present in both lists, basically. And set majority. This is interesting. Yeah, we are considering in this case, you see that we have 3 sets as the input. So you see that it takes the member which is present in all the 3 sets. You see that we have the list here from 0 to 9, and then we have 2 times the series 5 to 14 and 5 to 14. And you see that the elements 5 to 14 are exactly those that come out from the result of this set majority, because all these elements appear in the 3 sets more times than the other one. Okay, so for example, if I change, let's say, this to 10. Also, in this case, we always have this the superposition. Basically, 0 to 9, we have a duplicated values between 5 and 9 in this case, and then we have 10 to 14, and here we have 10 to 14 as well. Okay, but if we change this, for example, to 15, you see that the other values disappear, because the only values that appear more than once in this case are only 5, 6, 7, 8, and 9, because they are contained in both first and second list. So majority determines which value appear more frequently in the three sets of data here. And set union, which is quite obvious. This is taking the elements that appear at least one in both the set A and set B. So duplicated items are just deleted. Okay, so you see that here we have a list between 0 and 9, and here a list from 5 to 14. So elements between 5 and 9 are repeated, but you see that here they appear just once. So this is the union of the two series, of the two sets, without repetitions, of course. So one single list that goes from 0 to 14. Set union. Cartesian product is it's very interesting. Actually, it can be useful in advanced data manipulation. Here we have the classic two series, 0 to 9 and 5 to 14, and you see that Cartesian product is what it's doing is creating a new set of data, which is more complex. You see this continuous cable, which defines the data tree structure here. So what happens is that the first element of the product is actually the two first items of the two series, so 0 and 5. Then we have 1 and 6, 2 and 7, 3 and 8, and so on. Okay, so the Cartesian product is actually not a real product. Okay, it's not a multiplication. It's just a way of blending data together. Okay, which is absolutely useful in many occasions when working with data sets. What happens here, for example, if I set, because these two series have count set to 10. What happens is if I set this count to 5, for example, you see that Cartesian product gets angry, gets red, and it says that A and B must have the same cardinality. Else, it won't be able to calculate the so-called product. Okay, so let's give it back the 10 value here. This joint is actually a simple analysis. It takes two sets and understands if these two sets are overlapping or touch each other, or they are disjoint. So there is a separation in the values between the two sets of values. So for example, you see that we have the classical two lists, 0 to 9 and 5 to 14. Of course, they overlap from 5 to 9. So if I use this set here, disjoint analysis say that they are not disjoint sets. They overlap. But if I take this third series here, which starts from 20, so the first one ends at 9 and the first one starts at 20. So if I take these, then this joint says yes, they are disjoint sets. Okay, because there is a gap between the two. Okay, so false and true. What happens if this ends at 9 and then I take this and make it start at 10? Then you see that they are disjoint as well. Okay, because they don't have any coincident values. Of course, if I take this and set it to 9, then they are not disjoint sets. Let's give it back the 5 values, so we have the original configuration here. And member index. Now, member index is another very important component in data manipulation. It tells you how many times a value appears inside a set, inside a list. Okay. Now, the only thing is that even if you see here, this is a list of numbers, right? So 0, 1, 1, 2, 3, 4, 1, 5, 6, 1, okay? Even if this is a list of numbers, it's important to understand how this memory index work. So you see that, for example, I took a slider here because I want to detect how many times the number 1 appears in this series, in this list. But I had to pass this value here through a text component. So if I plug this directly to member, you see that the member index doesn't find any occurrence of this value inside this list, even if we see it here, okay? Because this is actually possible only if you provide a text value in the member index member input. And you see that once it recognizes exactly the value, it says index number 1, 2, 6, and 9 correspond exactly to this value here, which is 1. And the amount of times, the count of the occurrences of this number inside this list is 4. So these are two very important informations when dealing with data manipulations, okay? For example, if I take a series of which I am sure that it's producing numbers and not text, for example, and I try to use the slider here, you see that it doesn't find any occurrence of the number 1 inside the list. We should have 1 as an index and 1 as number of times the number 1 appears in this series. If I do it via a text component, then you see that everything works fine, okay? So this is how the member index works. It's very, very, very important component. And then there is this replace members. You see that same thing here. We want to find a specific value inside our list, which in this case is 1, always passing through a text component. And we want to replace this value here with this other value. And you see that from 0, 1, 1, 2, 3, etc., we pass to a 0, A, 2, 3, and so on. So it's actually same thing, but instead of simply detecting, you can replace items with this. And then subset. Subset checks if set B is contained inside set A. So set A is 0 to 9, set B is 2 to 5, and it's evident that the second set is contained inside the first one. If I take this and say I want 9, for example, this is false, because count set to 9 gets to the value number to the value 10, which is falls out from the first set of values. So that's why it becomes false. And now these other components here are, let's say, this is taking too long. I will skip something here. I will leave them in the shared definition, so you will be able to have these examples here and understand how they work. If you don't, you can just drop me a line and we will discuss this. But I will only focus on delete consecutive because it's somehow important and relevant in a standard Grasshopper workflow. So you see that we have a list with 0, 1, 1, 2, 3, 4, 1, 5, 6, 1, where we have repeating values here. 1 repeats 2 times as consecutive values. And this is actually deleting the consecutive values, just leaving one number 1 in this position. So this can be also very interesting. If you have duplicated data inside a list in 2 consecutive positions, then you can delete this. Why it's important, this thing? Because, for example, imagine that we are creating a polyline. Okay, so in case we create a polyline, it might happen that 2 points are coincident. If 2 points are coincident, Grasshopper is forced to understand that as the 2 points are coincident, a zero length segment will be created. So it has to eliminate this zero length segment in order to create a valid polyline. Now in this case, for example, the delete consecutive will delete the second point coincident with the first one, and then everything will work smoothly. Okay. So yeah, let's leave the remaining two component here at your investigation. And if you have problems, you can always contact me via social networks or the website. So that's it for the first three groups of command: list, sequence, and sets. And in the next session, we will be talking about trees. And then we will play around with this, with all these components here in order to create some kind of design using Grasshopper and data manipulation.